All right, so yesterday I gave you a little preview of what's next. We're going to have to get our calculators out and start using them again. So get them out, warm them up, press some buttons there just to let them know that you're ready. Okay, so every year I get this envelope from the city of Oak Ridge. And in the envelope, there is a little pamphlet that tells me about the quality of the water here at Oak Ridge. Every year, by EPA standards, they have to do this. They have to let us know. And what I've noticed every year is that there are some very, very, very dangerous, poisonous chemicals in our water. That's a fact. There is. Do I worry? No, I don't. Why? Because it's in very, very small amounts. How do I know? Because of the way they measure it. There are numerical values there. On that pamphlet, there are numbers. Okay? They aren't words, adjectives like very, very small, big, huge. There aren't. There are numbers there. Second hook here, second analogy. I love, I love him so much, but I only know him by Fluffy Iglesias. He's a comedian. What is his first name? What? Gabriel Iglesias. Okay, he's a Mexican comedian, very, very funny. If during lunch, during study hall, Kelsey, I want you to look up on YouTube Gabriel Iglesias Cuban coffee. Hilarious. Gabriel is like 300 pounds, maybe more. He's a big guy. So he does a comedy routine in Miami, and he's heard so much about Cuban food that he wants to try it out. Well, it's late at night. So he goes into the taxi, he goes, "Are there any Cuban foods? Any Cuban food restaurants open at this time?" And the cab driver says, "La Careta." I've been to La Careta. Very good food. Big chicken in front. Big statue of a chicken. We like chickens in Cuba. All right, so he goes there, and it is 11:30, and he's getting kind of drowsy, and he still has a ways to go. So he asks for some Cuban coffee. He's heard about Cuban coffee. He asks for some Cuban coffee, and so the waiter comes and brings him. If you've ever had Cuban coffee, it comes in these teeny tiny little cups. It's like the little cups you might have when you're playing with your little dollies. Little cups. So he gets the little cup and he looks at the waiter and says, "What is this?" And the waiter says, "Es un cafecito," that is a coffee, little coffee. And he looks at the waiter and goes, "Look at me. I am not a cafecito type of guy. I'm a cafezón. Give me more. I need more." And the waiter doesn't understand. He goes, "That's a cafecito. You don't want more." And Gabriel goes, "No, I want more. I need more." Not understanding why they gave him a little cup. Folks, we Cubans, we like everything to the extremes. So this American coffee, that's water. That's basically flavored water. You might as well just sell it as flavored water. When we drink coffee, we drink coffee. It's strong. I mean, that stuff, I didn't used to have hair on my chest, and then I started drinking Cuban coffee and the hair just started sprouting off. I made my wife stop taking Cuban coffee because too much hair. No, I'm kidding. She has no hair on her chest. I am kidding. It only works on guys. It only puts hair on the chest of guys. This stuff is strong. So, Gabriel is enough of a butthole that the guy comes back with a soup bowl full of Cuban coffee. And Gabriel, of course, goes, "That's what I want." So he takes the soup bowl full of Cuban coffee and takes a sip. And he said that it's like drinking motor oil. And then he realized why it's such a little cup. Because it's very, very strong. Very concentrated. Who's ever had espresso? Cuban coffee. You know what I'm talking about. That stuff will, if you just leave it there, pretty soon the cup starts to get away from you. That is very strong stuff. So he's there staring at the waiter who's now looking at him like, "I want to see you drink that." And he realizes he's got to drink it. So he starts chugging it down just to show the waiter what a big man he is. The waiter turns around, goes into the kitchen, and can be heard as saying, "Manolo, call 911." Because we Cubans, we have one volume, and that's loud. And that's why I am such a loud teacher, because I'm Cuban. All right, why? Well, Gabriel goes on to talk about how he was awake the rest of the night because of how much Cuban coffee he drank. But it all goes back to the same problem. Unless you have a numerical value, one person's strong coffee could be another person's weak coffee. Wednesday is our strong coffee day. My wife and I have this really, it's strong, okay? American coffee. Strong American coffee. Compared to Cuban coffee, it's still weak. So strong, weak, concentrated, dilute, those are not very accurate numbers because it depends on your point of view. Amy's idea of a strong coffee is very different from Sarah's idea of strong coffee. They can get in an argument, and we wouldn't know who's right because the word strong is just not good enough. So in chemistry, we do away with strong and weak, dilute and concentrated, and we add numbers to it. How are we going to do that? Well, you got a preview of it yesterday. Are dangerous stuff dissolved in water always dangerous to us? There's mercury in our water, but it's okay. It's in such teeny tiny amounts that it's not going to hurt us. How about stuff that's good for you or harmless? Could that hurt you? Actually, yeah. You can poison yourself with too much water. You can literally kill yourself by drinking too much water. And water is something that's good for us. So yesterday, we made differing concentrations of Kool-Aid. Some of it you found yummy, some of it you found yucky, and some of it you found too strong, correct? All right. So what we did in order to make sure that we understood their concentrations is we created numbers. Solution concentration is the amount of solute in a specific amount of, let's change that word to solution, not solvent. Solution is both the solute and the solvent together. So kill this word right here, cross out this word, or actually don't even write this word. Put solution on there. Solution. So, if I say I have a 5% solution, it's not 5 over 100, it's 5 over 105. I'm sorry, it would be 5, in this case it's 5 over 100 because the 100 is both the salt and the water together. And that was the key thing that I tried to explain to you. You always have to add the solute to the solvent. Always add the solute to the solvent. They already did that in this particular question, so this is a 5% solution. A 5% solution. So, how do we do this? Add the mass of the solute to the mass of the solvent, divide the solute by your new total, and then multiply by 100. So, a good example would be this one. What is the mass percentage of glucose in a solution prepared by dissolving 10 grams in 100 grams of water? Well, be careful, because you're going to want to say, oh, it's 10%, Mr. Moreno. No, it's not. It is 10 grams divided by the 100 grams of water plus the 10 grams. So it's 10 divided by 110 times 100. Let's practice. TA, thank you for volunteering. Let's do this first one. What is the numerator? The numerator is the number that goes on top. What is the denominator? Very good. It is 60 plus the 20 to equal 80. And what do we multiply this entire mess by? TA? So 20 divided by 80, I think that's 1/4. So thinking maybe 25%. Can you confirm that for me, TA? Times 100. So it's 0.25 times 100. 1 decimal place would probably be best, just to be consistent. Science loves consistency. Science loves consistency. All right. Thank you very much, TA. Great job. That's it. Senor Soria, do the next one for me. Letter B. What goes on top? 15G. What goes on the bottom? 115. So you passed the critical point. Yes, you always add this to the solvent of water. All right. Times what, Jorge? So 15 divided by 115 times 100 is? Don't forget your units. Is that right? Okay. Some people seem to be... We're good? What? What should it be? Oh, so it's 13.04? Oh, okay. So it's 13.0. He didn't even get up. How could he be tripping? All right. Allie. Next one. 30 grams. Times. So 30 divided by 150, that's like 3 divided by 15. That's like 1/5. So what's 1/5? Maybe 20%? 20%. Okay, be careful, because in your homework tonight, there's going to be one that's going to be tricky. It's going to say this.
Wait, homework?
Well, it's not homework, it's classwork. It's going to say this: 30 grams of sugar in 120 grams of solution. Ooh. That change of wording changes everything. Because what is a solution? A solution is the solute plus solvent together. So whenever you see that 120 grams of solution, you don't have to add 30 to 120. That's it. 120 is your denominator. Okay? That's a bit tricky. You know how I always like to throw in at least one tricky question. So solvent, when you see solvent or water, you do add. But when you see the word solution, then you don't add them together. Now, the rest here is just practical stuff that you need to understand in order to be a good citizen. When the city of Oak Ridge gives me that pamphlet, the numbers that are there are in these units, parts per 100. So 5 parts per 100. Imagine 100 ping pong balls. They're all white. 5 of them are orange. So if you have a solution, then out of that 100 ping pong balls, you have 95 white ones and 5 orange ones. Believe it or not, for contaminations of water, that's actually pretty contaminated. That is a contaminated amount of water. So typically, you're going to see it in parts per 1,000 or even parts per million. For example, mercury, it's in our water, but it's in parts per million. That means you have 1 million ping pong ball, and if you have 1 part per million, you have 1 orange out of that million. Are you even going to see it? No. And typically mercury is in even decimals of parts per million. So it'd be like parts per billion. Yes, it's there. The chances of it affecting you are microscopically small. Microscopically small. So, what is a good way of picturing how anything dissolves in water? Like a tug of war. Water is very good looking. The oxygen on water is like, ooh, wow, very good looking. The hydrogens on water are very good looking. So for most things, when they encounter water, very nice, very good looking. Okay? So, let's see. Anybody here in a relationship? Sarah. Boyfriend, girlfriend, what is it? Oh, that's probably texting you right now. Leave it alone. What is it? Your boyfriend. Okay, so he's pretty good looking? Yes, he's very good looking. Okay? So, Sarah and her boyfriend are, let's say, at a restaurant. And sitting right next to Sarah is Chad Tatum. Good looking? Yes? No. Okay. Tell me a movie star, TV star that you think, oh my. What? No, I don't have time for guesses. Go. What? Iron Man. What? Robert Downey Jr. Oh my gosh. You like old people. Robert Downey Jr. Okay, so you're there having dinner at Sonic with Robert Downey Jr. Or not with Robert, with your boyfriend. And then you see Robert Downey Jr. come in and order and then look at you and wink at you and then say, hey, can I sit with you guys? And then he sits with you guys. And then it's like your boyfriend does not exist. He just turns to you and wants to know everything about you. What happens if he goes, hey, how about you, me, and my Ferrari? What would you do, Sarah? Would you go, yes, Robert Downey Jr., I will ride with you on your Ferrari? Or will you go to your boyfriend, no, I'm dating him, and no, I can't break up. What would you do?
I'm not getting that Ferrari.
You're not? What? She lies! Yes. Okay, so that is a perfect example of why water can dissolve most things. Water is both a combination of Robert Downey Jr. and Taylor Swift. Okay, so one side is Taylor, who's going to be very attractive to certain people, and then the other side is Robert Downey Jr., that really old guy, who's going to be attractive for Old women and Sarah. All right.
Oh my God.
So, why is water an exceptional dissolver of ionic compounds? See, what she's afraid is that he has spies here in this classroom, and it's one of you spies are going to tell him that she would prefer Robert Downey Jr. to him. Even TA would go, I would get on the Ferrari with him. Water is very polar. For now, just think of polar as very attractive, very polar. It has an oxygen part, which is like very negative. And it has a hydrogen part, which is like, oh my goodness, very positive. All right, so the last thing you need to do is, what I would do is make these drawings. Ready? Not that one. Here is water. Pretty good looking, huh? Look at that oxygen. Ooh. Amy's going, that oxygen's very good looking. And then Carter over here is going, oh, look at those hydrogens. Very good looking. All right, so here is Amy and Carter, and they check out the water molecules heading toward them. And, ooh, notice that Amy has connected right there, right here. Amy has told Carter goodbye. Amy has told Carter goodbye, and now she is connected to that big fat oxygen molecule. But that's okay because Carter is going, oh, baby, hydrogen, come here. So, little by little, they get taken apart until Carter and Amy are no more. Carter and Amy are completely surrounded by water. What? That would be nice because you're gonna have to draw it for your work, for your homework or classwork. Okay, draw a bunch of crystals with water heading toward them. Did you not get the notes? They're over there.
I do.
You just
Don't have a pencil. You singing this whole time with that pencil?
Okay, so you have a bunch of crystals with positives and negatives and water heading toward them. And then make sure you draw something like this where the oxygen part of water, which is the big fat circle, is taking apart the positive, and the little circles in water are taking apart the negative. And then finally, you have this, with water completely surrounding the individual ions.
You want that drawn too?
No, kids, chill out.
Yeah. First off, you didn't specify what.
Draw it in such a way. I would draw this one, and this one. Draw it in such a way that you understand. Here, let me give you a simulation that maybe it'll make it even more obvious. Okay, so here's
Sodium
salt.
chloride crystal.
Okay, notice the little gray ones. That's Amy. And the big fat green ones, that's Carter. Watch what happens.
Crystals are held together by attractive forces between the positively charged sodium and
Okay, so when they're the only people in town, then of course Carter will be dating Amy and will be happy.
negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of
But look what happens here. Okay, this is Carter right here. Let me use my pointer. This is Carter. Okay, And notice you've got Taylor Swift right there. Taylor Swift are the white part of water. Taylor Swift, and Carter's going, whoa, Taylor Swift wants me. Amy, you're kind of good looking, but this is Taylor Swift. Watch what
Polar
happens.
water molecules attract
what
the
happens.
negatively charged
Up,
chloride
come here,
ions
Carter.
and gradually
Come
surround
here,
them.
Carter. Ooh, Carter.
Likewise, the oxygen ends of water
That's okay, because here, now you see Amy, which is this gray blob here, and Amy's going, oh my goodness gracious, there is Robert Downey Jr. Okay, give me somebody.
Let's do Captain America.
What?
Captain America?
Chris Evans. Chris Evans. Okay, so there's Chris Evans, and all these Chris's are going to Amy. Come here, Amy. Dissolve with us.
molecules are attracted
Watch.
to and surround the positively charged sodium
Oh,
ions.
look.
The hydrated
Come
ions
here.
drift away into the
Here, you
solution,
can hold my
allowing new
shield.
water molecules to surround newly exposed ions.
And the whole thing
Gradually,
happens over
the
and
entire
over.
crystal dissociates
So now you know what dissolving looks like. Congratulations. Now you should be able to do worksheet 6.2.